So text mining systems used to be something very expensive to build. Only governments could afford. Back in the 90s, it was something that was used for intelligence agencies, large corporations, and so on. But over the last 10 years, this has become a commonly used application technique that's used all over the place. Financial applications, scientific applications, basically almost everywhere you have text documents, you can make use of automated processing. And the reason this has become more widespread is that the technology for building this has become a commodity. So there is a lot of available open source software where you can quickly and easily build NLP systems, including text mining systems. So let's look at how do you do that? How do you build a system like this, like the European Media Monitor for analyzing news, or a system that looks into scientific articles? So you can imagine that first there is a lot of boring infrastructure work you have to do, because you have all of these documents coming in, but they come in different formats. It could be text, plain text, like in an email, but it could also be HTML, XML, PDF, a Word document, and it can come from different sources. It can be in the file system, in a database, over the network, and so on. And you have to convert and load these documents into your system. So that's not really exciting, but as you'll probably see or have already seen, a lot of the work in AI is not the cool, exciting work that you think about. 80–90% of the work that you do is boring stuff like cleaning up data and dealing with stuff like loading, transforming, cleaning up your data. So once this is handled and you have your documents loaded, you're starting to analyze it. So for example, in the news analysis, you'll find information about events and people and what people have said. So now you also have to store these so-called annotations. So for example, if you extracted a person in a specific document, in a specific location, you have to store this information together with the document. And again, you have to keep track of it. You have to be able to find out the position in the text. When you later click on something like a quote, you want to know where it came from. So you have to deal with this annotation handling. And the way this is done is so-called standoff markup, meaning you have something like an XML representation of the text, and then in a separate part, you have sort of pointers into the text with these annotations. So to get these annotations, you have to process the documents. We talked about this a little bit in the previous week, like tokenizing a text, finding part of speech tags, parsing, chunking, lemmatizing. We'll talk about this more today. So again, these are more or less standard tasks, and you don't want to implement all of these from scratch. Now you want to have some kind of library, so you can just use them and build the system on top of these existing tools and libraries. These tools in turn need various resources. So because we are dealing with natural language, a lot of what these tools do is language dependent. If you try to find part of speech text for English, this is different from processing a French document, Spanish, German, Chinese, what have you. So you need resources specifically for the language. For example, the lexicon of words in that language, grammar rules for that language, and so on. A lot of these tools work with machine learning. So of course, you can train these machine learning models yourself using a corpus of documents. But again, if you want to just start, you would like to have a pre-trained model that you can just load and start processing. And then finally, we talked about evaluation, precision recall, and so on. So this is, again, similar to what we talked about in machine learning. You have to be able to understand how well it works, what the performance is, precision recall, and so on. So you don't want to write code for computing these metrics from scratch either. You want to have them available that you can just run something and then compute these various metrics like we have done in the lab with scikit-learn. So the good news is, as I've mentioned, nowadays there is a lot of robust, mature open source software available to build this type of system. So you can roughly classify them into these three categories here. We have individual tools in the sense of a tool that does a specific task. For example, doing parsing, doing part-of-speech tagging, tokenization, and so on. Now, for having a complete system, obviously it's not enough to do one step. You need to combine these tools together. Now you have to run a tokenizer, a part-of-speech tagger, a parser, and a few other steps. So for integrating these tools together, there are various frameworks. I'll show you some of them in a couple of slides. And then finally, you need resources. Yeah, just like the word lexicons specific for a language, pre-trained language models, word nets, grammar rules, and so on. So what are your options for developing NLP text mining? So there are sort of the big frameworks on the one side, and on the other side are smaller libraries. Frameworks are integration environments where you can plug in lots of individual tools, orchestrate them, and they have a graphical development environment that allows you to run the tools, run evaluations, and so on. And the two major ones in this area are GATE and UEMA. GATE stands for the General Architecture for Text Engineering. This is an academic project that has been running since 1995 at the University of Sheffield in the UK and has been funded with millions from European Union research and also industry projects. Another one that's very widely used is UEMA, which stands for Unstructured Information Management Architecture. So that's a system that was developed by IBM, and IBM open sourced it in 2007. So this is now available as an Apache project. And you've seen UEMA in use. We talked about Watson a couple of times, and Watson is an example for a system that's built on top of UEMA. So both of these are open source. GATE is available under the LGPL and UEMA under the Apache license. So these are the big, heavy frameworks. On the other hand, are libraries. So the difference between a library and a framework is that in a library, you code using the library, you call functions directly, and in the framework, it's orchestrated by the framework. The framework calls the various functions, and you basically write plugins for that framework. And you'll see that these two frameworks, they make use of all of these libraries. There are libraries written in Python, in Java. NLTK is a very well-known one. Core NLP that comes out of Stanford is another one that's written in Java. And these all integrate with these frameworks here. On the other hand, it also works the other way around. GATE, for example, just had a Python wrapper added, so you can call GATE, which is Java, from Python as well. So this is something that has been in development, as you can see, over the last 10, 15, 20 years. What's a bit more recent over the last 5 years or so is increasing use of deep learning also for natural language processing. So deep learning started on speech processing, on image processing, really became mainstream more than 10 years ago, but it's still relatively new for natural language processing. And a bit later in the course, we'll understand why. We'll talk about deep learning for NLP, and you'll see why it is more complicated, more involved than processing images, for example. But this is the latest trend. Over the last couple of years, more and more people experiment with using deep learning for NLP. So the typical deep learning frameworks like Torch with a Python wrapper, PyTorch, or TensorFlow are now also being used for natural language processing. So going back to the frameworks, here's an example for how your email looks like. So this is actually built on top of Eclipse. So it looks just like a software development environment. Now you have, when you work with an Eclipse IDE for working on code, you have all your files, your source code. You look at one in example in detail, and then you have various tools that provide you information like variables and so on. And now when you work with natural language processing, it's kind of the same thing. You have your tools that you work with, for example, for finding entities. You have the document you analyze and then various information about it. Gate looks somewhat similar. Again, you have the document that you're working with. You have various resources that you run on these documents, individual tools and pipelines, and then information that were extracted from the document. So, for example, here, some entities that are selected, like an organization or a person, and then various information that you can see where it was detected in the text and additional information about it. So let's look at how this works. One of the nice things about Gate is that as an open source project, an academic project, it comes with a lot of available tools, resources, and example pipelines. UEMA, in the beginning, when IBM open sourced it, they just open sourced their framework. They didn't open source any of their plugins to do something with it. Now they still want to make money with it. Gate, on the other hand, it has been available for so long that you can start right away with a lot of existing tools. So here, what you can see is the view of a pipeline, meaning a number of processing steps that are run one after the other on the document. And you can see that you can swap out and rearrange these steps in the pipeline. So you basically have a collection of tools that you can just load from a repository. And then without any programming, just by moving tools in and out, you can compile a pipeline of processing steps, rearrange steps in the pipeline, for example, swap out one component for another to try out a different approach, add additional processing steps, and so on. On the bottom, you see for a specific component, various parameters that you can set. So you can configure and run a pipeline of NLP components without doing any programming. Of course, if you want to write a new component that does something very specific, you have to do programming, but a lot is more data-driven analysis, configuration of these pipelines. So what you see here is one of the example pipelines that come with the system for finding entities in a document. So let's, entities, something like a person, an organization, money, date, location, and so on. So let's look at how this actually works, how we get from a document to finding these entities using these steps in a pipeline. So you can see the first step, this is just a resetting resource. Basically, when you run it a second time, you want to clean the results from the first run. So this is just a very basic reset component. The first step that actually does something is the tokenizer. We talked about tokenization briefly last time. What you do is you break up a stream of characters into individual tokens. So in Gate, there are a couple of different tokenizers. One of them is working with rules. So if you look into it, it's basically regular expressions. And there are different rules for different kinds of tokens. For example, tokens that are number tokens, tokens that are combining different white space characters, and so on. So you can see after running the tokenizer on the document, it will add as annotations a whole bunch of these tokens. You can see start and end offset. So these are pointers into the text. Starts at character 158, ends at character 163. You have specific kinds of tokens, space token, word token, punctuation token, and so on, how long the token is, and some additional information. For example, is it all in lowercase, all in uppercase, mixed case, and so on. So that's the first step. And as I explained last time, tokenization can be tricky in practice. Once you have these tokens, you can do the next step in the pipeline. So going back here, we've run the tokenizer. I'm skipping over these for the moment. Let's look at the part of speech tagger next. Part of speech tagging means assigning the part of speech to each token. So part of speech is something like finding out, is this word a noun, a verb, an adverb, an adjective, and so on. So this is done with a part of speech tagger. And again, there is a standard component that is included with Gate, the so-called Happel tagger. And what it does is it goes over these tokens and then finds out using, well, I'm not explaining in this course how this works in detail, but most of these work with machine learning. They are trained on a corpus where you know the tokens, and then it learns statistically what is the most likely token for a word. If you take an NLP class, you learn how this works in detail, how this is implemented, and how this is assigned. But for our purposes, basically see it as a machine learning problem. So this is already trained. We can just run it, and it will tell us this word is a noun, this word is a noun singular, and so on. So at one point, once we've done all of these individual processing steps, we want to find named entities. So a named entity is something like a person, an organization, a location, and so on. So it's a specific type of entity. And again, there are different approaches. We'll talk about these more in detail later. One approach is having rules that look at all the results we got previously. So the tokens, lookup information, the part of speech tags, and then have a number of rules that say, okay, if there is specific token string followed by a specific part of speech tag, then this must be a person. So let's look at an example here. It detected that Dr. Henry Buchwald is a person. It also found out that this person is male and that this person has a title. So let's see how this works, how the system found this out. In the example system, there is a whole bunch of rules. And again, these are somewhat similar to regular expressions, with the difference that when we talked about regular expressions last time, we were working on a stream of characters. But here, these annotations form a graph. So basically, it is, regular expression matching over a graph. This is also called a transducer, which sounds pretty cool, right? So you can see here, there is a rule for a person with a title. And you basically have, if the token category is one of these three part of speech tags, and it's followed by something that's a title, where a title is something like professor, doctor, and other titles, which comes from a lookup list, combined with a first name, initials, and a few other options. Then when this rule matches, the corresponding span of text is annotated as a person. And this is just one example of a person rule. There are different types of person rules: person with title, without, with initial, without initial, and so on. And all of these will try to match the document and annotate persons. And then there are rules for all of these other entities. Rules for dates, for addresses, for organizations, for locations, for emails, for IP addresses, and so on. And all of these are run over the document and generate these annotations. So try this out. There is an online demo available for Gate. And then I will see you again in the next lecture part.